This one.
Hello. Let us see the second chapter of Functional Analysis 1. Let us see the titles. The syllabus is Basic Properties of Finite Dimensional Nonlinear Spaces and Compactness. Second title is Weak Convergence and Bounded Linear Transformations. Third title is Nonlinear Spaces of Bounded Linear Transformations. And fourth title is Dual Spaces with Example. Let us see the first title. You have to write the name of chapter as well as first title and then the definitions. First definition is basis of vector space. A linearly independent subset of a vector space capital X which spans X is called basis of vector space capital X. Dimension. Number of elements in basis is called as dimension of vector space. Finite dimensional vector space. Number of elements in basis are finite, then the vector space is called as finite dimensional. Subspace. A subspace of a vector space X is a non-empty subset Y of X such that for all y1, y2 belongs to Y and all scalars alpha, beta, we have alpha into y1 plus beta into y2 belongs to Y. Hence, Y is itself a vector space with two algebraic operations being induced from X. Norm linear space. A norm space is a vector space with a metric defined by a norm. Norm. A norm on a vector space capital X is a real valued function on capital X whose value at a point X belongs to capital X is denoted by norm of X such that it satisfies properties norm of X is greater than or equal to 0. Norm of X is equal to 0 implies and implied by X is equal to 0. Norm of alpha X is equal to mod of alpha into norm of X. Norm of X plus Y less than or equal to norm of X plus norm of Y. X and Y are vectors in X and alpha is a scalar. A norm on vector space X defines a metric D on X given by distance between X, Y is equal to norm of X minus Y. Thus, every norm linear space is a metric space also. Closed set. A set which is equals to its closure is called as closed set. Limit of every sequence of a closed set lies in that set. Equivalent norms. Two norms are said to be equivalent if they generate the same topology, that is, open subsets of norm linear space X are same in cases of both norms, with respect to both norms. Let N be norm linear space, then norm 1 and norm 2 are defined on N are equivalent if and only if there exist positive real numbers small m and capital M, such that small m into norm 1 of x less than or equal to norm 2 of x less than or equal to capital M into norm 1 of x for all of x belongs to capital N. N is a norm linear space. Like as we have seen different types of metrics on a metric space. Similarly, there may be different types of norms on a norm linear space, like as norm 1, norm 2, and etc. Let x1, x2 to xn be linearly independent set of vectors in norm linear space capital X of any dimension. Then there exists a number c greater than 0 such that for any choice of scalars alpha 1 to alpha n, we have norm of alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn greater than or equal to c into in bracket mod of alpha 1 plus mod of alpha 2 plus mod of alpha 3 plus and so on plus mod of alpha n, and here bracket complete. This is absolute lemma. This is in first chapter. Compact subset. A subset M of a metric space is said to be compact if every sequence in M has a convergent subsequence whose limit is an element of M. Convergent sequence. A sequence Xn in a norm space capital X is convergent if X contains an element small x, such that limit n tends to infinity, norm of xn minus x is equal to 0. That is, xn converges to x. Next definition is Cauchy sequence. A sequence xn in a norm space X is Cauchy if for every epsilon greater than 0 there is a number capital N greater than 0 such that right here greater than 0 such that norm of xm minus xn less than epsilon for all m comma n greater than n. We have to write some notes. First note is Bolzano-Weierstrass theorem. It states that every bounded sequence has a convergent subsequence. Next theorem is every finite dimensional subspace Y of a norm linear space capital X is closed in X. Next is Reed's lemma. This is also in first chapter. It states that let Y and Z, capital Y and capital Z, be the subspaces of a norm linear space capital X of any dimension, and suppose that Y is closed n is the proper subset of Z. Then for every real number theta in the interval open interval 0, 1, there is an element small z belongs to capital Z such that norm of z is equal to 1 and norm of z minus y is greater than or equal to theta. All of y belongs to capital Y. These are all the definitions to study the theorems under the first title. Also, we have seen a norm on a vector space can be restricted to its subspace. So, a subspace of a norm-linear space, also called as norm-linear space. First theorem is every finite dimensional subspace Y of a norm-linear space is complete. Proof. Let capital X be a norm-linear space and Y be its finite dimensional subspace. That is, dimension of Y is equal to small n, less than infinity. That is finite. Consider any Cauchy sequence Ym in Y. We have to show that Y is complete. So that we show any arbitrary Cauchy sequence Ym in Y is convergent. That is to show limit m tends to infinity Ym is equal to Y belongs to capital Y. Let E1, E2 up to so on En be a basis for capital Y. Then each Ym can be expressed as, that is, each term in sequence Ym can be expressed as Ym is equal to alpha 1 m C1 plus alpha 2 m C2 plus and so on alpha n m Cn. We gave this equation number 1. Since the sequence Ym is a Cauchy sequence, by definition we have for all of epsilon greater than 0, there exists an integer capital N, such that small m greater than n and small n greater than n. This implies norm of Ym minus Yn less than epsilon. We give this equation number 2. As E1, E2 to En is a linearly independent finite set of a norm-linear space capital X. Of a norm-linear space capital Y. This is the basis for capital Y, so it is linearly independent. E1, E2 to En is a linearly independent finite set for in capital Y, in a norm-linear space capital Y. So we can apply absolute lemma. Now epsilon is greater than norm of Ym minus Yn because Ym is a Cauchy sequence. So we prove norm of Ym minus Yn less than epsilon. Hence epsilon greater than norm of Ym minus Yn is equal to norm of summation j is equal to 1 to n in bracket alpha j m minus alpha j n into ej. we have written ym and yn as a linear combination of elements in basis where scalars are alpha j m for ym and alpha j n for yn, and then ej taken common and outside the bracket. This is greater than or equal to c into summation j is equal to 1 to n mod of alpha j m minus alpha j n. This is by absolute lemma. So epsilon by c is strictly greater than c taken to left hand side. Summation j is equal to 1 to n mod of alpha j m minus alpha j n. Give this equation number 3. So summation j is equal to 1 to n alpha j m minus alpha j n less than epsilon by c, less than epsilon dash, where epsilon dash is equal to epsilon by c. This shows that each of the sequence alpha j m is equal to alpha j1, alpha j2 up to so on alpha jn. For every j, we get a sequence. When j is equal to 1, then alpha 1, 1, comma alpha 2, 1, and so on alpha n1. This is a sequence. For j is equal to 2, we get another sequence. For different values of j, we get different sequences. And each of this sequence, each sequence is a Cauchy sequence. Hence, it is convergent. From this equation, summation j is equal to 1 to n mod of alpha jm minus alpha jn less than epsilon dash. Hence, each term is less than epsilon dash. So that it is shown that alpha jm is a Cauchy sequence for each j. But alpha j are scalars from scalar field. And the fields are capital or capital C, and they are complete. Hence, every Cauchy sequence is complete if the Cauchy sequence belongs to the scalar field K, which is either R or C in this paper, functional analysis. So, let alpha j be its limit. That is, alpha 1 will be the limit of alpha m1. Alpha 2 will be the limit of alpha m2. For different values of j, we get simultaneously different limits. Now we define y is equal to alpha 1 e1 plus alpha 2 e2 plus and so on alpha n en belongs to capital Y. Consider norm of phi m minus y is equal to norm of summation j is equal to 1 to n alpha jn minus alpha jn into eg. Here n is the lower suffix of e. Now consider norm of ym minus y is equal to norm of summation j is equal to 1 to n in bracket alpha j m minus alpha j n into eg less than or equal to summation j is equal to 1 to n mod of alpha j m minus alpha j n into norm of eg. This is less than epsilon dash. Because summation over j is equal to 1 to n mod of alpha j minus alpha j n. This is less than epsilon dash. We have proved this. Limit m tends to infinity, ym is equal to y. You can prove this by another method also. Clearly, y belongs to capital Y because scalars are from the field and elements of basis and elements even to n are elements in basis of Y. So y belongs to capital Y. As ym was arbitrary Cauchy sequence, and we proved that it is convergent. Hence, every Cauchy sequence is convergent in Y. So Y is complete. Hence, the theorem is proved. Hence, it is proved that every finite dimensional subspace Y of a norm-linear space is complete. Next, we see a definition, compactness. A subset M of a metric space at X is said to be compact if every sequence in M has a convergent subsequence whose limit is an element of M. This definition we use as for sequentially compactness also. But as this is every norm-linear space is a metric space, so we can use this definition also. Every sequence in M has a convergent subsequence whose limit is an element of M. Theorem. In a finite dimensional norm-linear space X, any subset M of X is compact if and only if it is closed and bounded. Proof. Let capital X be finite dimensional norm-linear space. Hence it is metric space. Let M be a compact subset of capital X. By result of metric space, every compact subset of metric space is closed and bounded. This implies M is closed and bounded. Conversely, M is closed and bounded. To prove that M is compact, let dimension of capital X is equal to small n, and let E1, E2 up to so on En be the basis of capital X. Now consider any sequence xm in capital M such that xm has unique representation. xm is equal to alpha 1 m e1 plus alpha 2 m e2 plus and so on alpha n m. Here upper suffix is m into en. Because m is subset of capital X and for x we have this basis. So xm is written as the linear combination of elements in basis. Alpha 1 m up to so on alpha n m are scalars. Since m is bounded, we assume that m is closed and bounded and proving that it is compact. That is, every sequence has a convergent subsequence. This is sequence xm. We prove that it has a convergent subsequence. Since m is bounded, sequence xm is bounded sequence. M is bounded, hence norm of every element in M is less than or equal to some constant k. And xm is a sequence in M. So norm of every element in xm is less than or equal to some constant k. Here we have written. Hence xm is also bounded sequence. Now k is greater than or equal to norm of xm is equal to norm of summation j is equal to 1 to n alpha jm into ej. Because we have written xm as a linear combination of elements ej and alpha jm are scalars. But ej is a linearly independent finite set in non-linear space capital X, so that we can apply absolute lemma here. So norm of summation j is equal to 1 to n alpha jm into ej. This is greater than or equal to c into summation j is equal to 1 to n mod of alpha jm. This is by absolute lemma. Say it's some constant. Now summation j is equal to 1 to n mod of alpha jm less than or equal to k by c. C we have taken to left hand side. We give this equation number 1. Now as summation j is equal to 1 to n mod of alpha jm less than or equal to k by c. Hence each term in that summation will be less than or equal to k by c. That is mod of alpha jm is less than or equal to k by c for each j. Hence it is less than or equal to epsilon dash. Let epsilon dash is equal to k by c. Hence alpha jm is bounded sequence. Alpha jm, j is equal to 1 to infinity or over j. You can write here lower suffix j is bounded by Bolzano-Weierstrass theorem. For bounded sequence we have alpha jm has a limit point. That is, it has a limit. It has a convergent subsequence. This bounded sequence will have a convergent subsequence. And let alpha j be the limit of that convergent subsequence. So for different m, different values of m, we have different bounded sequences like as alpha 1j, alpha 2j, alpha 3j, And every sequence has a convergent subsequence which has a limit alpha j. That is, alpha 1j will have limit alpha 1 1. Alpha 2j will have limit for different values of j only we have the limit. That is, alpha 1j, this sequence will have limit alpha 1. Alpha 2j will have the limit alpha 2. In this way, we get a set of limit alpha 1, alpha 2, and so on. Therefore, xm has a convergent subsequence, let zm, which converges to z. Consider element z is equal to summation j is equal to 1 to n alpha j ej, where alpha j are the limits of sequences alpha j m. When you read this, you will get cleared. Now as capital M is closed, so Z belongs to capital M. This shows that a sequence xm in capital M has a convergent subsequence which converges in M. Hence, M is compact. Hence, proved. When you read this theorem, you will get cleared. Next theorem is, if a norm-linear space capital X has a property that the closed unit ball capital M is equal to set of all small x belongs to capital X such that norm of x is less than or equal to 1. It's compact. Then capital X is finite dimensional. Proof. Let capital X be a norm-linear space. Let M is equal to set of all x belongs to capital X such that norm of x is less than or equal to 1. Let this set be compact. We have to show that X is finite dimensional. We assume that X is infinite dimensional norm-linear space and prove that it is wrong. We assume that dimension of X is equal to infinity. Now we choose an element x1 of norm 1. Then x1, an element x1 in then x1 generates a one-dimensional proper closed subspace capital X1 of capital X. Capital X1 is proper closed subspace of capital X. So that we can apply Reed's lemma. As we assume dimension of X is equal to infinity and X1 is proper closed subspace of capital X. So that by Reed's lemma there is X2 belongs to capital X of norm 1 such that norm of x2 minus x1 greater than theta is equal to 1 by 2. Next, x1, x2, these two elements generates a two-dimensional subspace capital X2 of capital X. Here, capital X2 is also proper subspace of capital X. By Reed's lemma, there is an element x3 of norm 1 such that Norm of x3 minus x greater than 1 by 2, all of x belongs to x2. This is for all of x belongs to x2. Now x1 and x2, this also belongs to x2. So that we can write norm of x3 minus x1 greater than 1 by 2. Similarly, norm of x3 minus x2 greater than 1 by 2. In this way, we obtain a sequence xn of elements of capital X such that we take here theta is equal to 1 by 2. Theta belongs to open interval 0, 1. So we take theta is equal to 1 by 2. We have to take theta from open interval 0, 1. In this way, we obtain a sequence xn of elements of capital X such that norm of xm minus xn greater than 1 by 2. M is not equal to n and m is greater than n because x3 is greater than x2, x3 is greater than x1. In this way, obviously, this sequence xn cannot have a convergent subsequence because this sequence cannot have a subsequence which is a Cauchy sequence because this sequence itself is not a Cauchy sequence. And we know that every convergent sequence is a Cauchy sequence. A Cauchy sequence may or may not be convergent, but every convergent sequence is a Cauchy sequence. And by definition of Cauchy sequence, it should be norm of xm minus xn should be less than epsilon. But here it is greater than 1 by 2. So as it cannot have a Cauchy subsequence, so it cannot have a convergent subsequence. This contradicts that M is compact. Because if M is compact, then every Cauchy sequence should have a convergent subsequence. Not only every Cauchy sequence. Actually, if M is compact, then every sequence has a convergent subsequence. Now this is a sequence we got which cannot have a convergent subsequence. So this is a contradiction that M is compact. So our assumption that X is infinite dimensional is wrong. Hence, X is a finite dimensional non-linear space. Here we have completed some theorems. In next lecture, we see one more theorem under this topic. In this way, under each title, we see definitions as well as theorems. Thank you.